Hello, welcome to the second day of lecture for chapter 21. I almost said chapter 2 because I have it. Today we're going to finish looking at capacitors, which is where we left off. Just a reminder, there is homework due tonight, unless of course you're watching this video later on YouTube. So there's homework due on the 9th, at the night of the 9th, depending on what day you're watching this. If you're watching it on the 9th, there's homework due tonight. If you're not watching this on the 9th, there was homework due on that night. Also, don't forget you have lab due on the 10th. So on the 9th, homework due at 11 p.m. On the 10th, lab due at 3 p.m. I am going to finish this chapter today. Friday will be example problems, which amusingly very few people watch that video, so I'll have to send an email about that sometime. Or just see how people do in exams and say that's what you get, because that's the way things are. But I'm going to jump in. What we were talking about was how the electric potential difference, more commonly called, or electric potential difference, which is the change between the electric potentials. Electric potential, more commonly known as voltage. And a device to store said voltage called a capacitor. And we introduced the parallel plate capacitor, which is two parallel plates, each with a different charge that allows us to store the charge and create a voltage. But the whole thing I was saying is these two parallel plates have a charge, and the charge can be used to create. The two parallel plates have a charge, giving them a potential difference over them. The potential difference we can use. But what I haven't talked about is how the hell do you apply the charge, right? So I said it gains a potential difference if it gets a potential difference, it gains a charge, but how are we even doing that? And the general idea is if you would want, and checking something. Okay, if you want to charge a capacitor, aka take your capacitor and make it so that there actually is a charge on the two plates, this one is not charged. This one would probably knock me on my ass if it was charged and I touched it like this. What you have to do is you have to hook it up to a battery or some other power supply that has a steady potential difference. And if I hook my parallel plate capacitor to a battery, as you see in this photo, basically if I hook one end to a positive terminal of the battery and the other end to a negative terminal of the battery, it's going to cause a movement of charge. And what will happen is whatever plates attached to the positive charge will become positively charged. Whatever plates attached to the negative charge terminal will become negatively charged. This is just charging by conduction, like we talked about last chapter. And so you can take a parallel plate capacitor and add charge to each plate. Once you add charge to each plate, then they will have an electric potential difference, aka a voltage. Now I'm saying the best way to charge a capacitor is to hook it up to a battery, but really, a battery? They traditionally were just made out of capacitors. Modern batteries are more modern batteries, but not up-to-date batteries, were made with a series of acid that was continuously causing a charge with chemical reactions. More modern batteries, like lithium ion and stuff like that, is the same idea that different compounds that's going to force a movement of charge. But the idea of how to charge the capacitor is still the same. You hook it up to something that causes a charge by some other means, and one end will become positive, one end will become negative. Now, we already said that capacitance was based off the physical construction of the capacitor, that the capacitance of any capacitor is the permittivity of free space times the area of each plate over the distance between them. And if you, we can, for each capacitor, say the amount of charge it will hold will go as CV. Q being charge, C being capacitance, and V being that electric potential, more commonly called voltage. What this means is depending on any given capacitor's shape and construction, we can define exactly how much charge it can store by applying a set amount of voltage. And that's usually what capacitors are used for. Capacitors are a way to just hold charge or create a voltage. A capacitor like this would be used to gain a lot of charge and being able to release a lot of charge very quickly. We're going to eventually talk about railguns, because that's the thing we talk about. And I have a friend who in undergrad made a railgun for a science class, not just for fun, but actually for class. And he used capacitors to dispel it because it could lose all the charge on here basically at once. That's the idea, that they can store charge and then use it for various means. Really, the practical use of a capacitor and something like that, we really can't get into though till next chapter. And really, over the next few chapters, we'll do it more, but not quite yet. One way capacitors are used is that's how mechanical keyboards work. Um, Not all keyboards use this, but some do. The general idea of a capacitor on a keyboard is that you have a metal plate, some substance, and a top metal plate, and that's what the key pushes down on. And between those two metal plates, it's just a capacitor. What happens is when you press down the key, you squeeze the area in between. But when you squeeze the area in between, you're changing the distance between the plates. By changing the distance between the plates, you're changing the capacitance. And the computer can detect that. That is one of the ways, yeah, keyboards can work. So there's a practical use right there. But here's the important thing. When you go and you put your potential difference over your capacitor, or your electric potential difference, I should say, and you add charge to it, what you're doing is you're getting it ready to do something. It has a change in charge, one positive side, one negative side, although this is really like donuts and rings for this type. That can be used to create things. But we've already talked about Monday how electric potential difference, or electric potential, if it's not the change in, can be related to energy. And we related energy and potential difference, aka voltage. And see, here's the idea, the thing with a capacitor is a capacitor is what it really is good for, what it really works for, is as you apply voltage and it gains a charge and gains a potential difference, it can store energy. And that's really what you want a capacitor for. Capacitors are something that can store electric energy for use later on. Now, you can find the potential energy inside a capacitor, but that's not normally something anyone will ever care about. What you really want to do is, if you charge a capacitor, to know exactly how much energy it stores. And we're going to see this as how much energy it can store to use for something else. Now, when we talked energy in physics 1, we used a lot of different terms, right? E was energy, Ke was kinetic energy, Pe was potential energy, which we've been using. But we also, if you remember with thermodynamics, we had U. Well, U was internal energy. Here we're going to use that U again and say that the energy stored in a capacitor, the internal energy of that capacitor, which I'm seeing if this even has energy written on it. Nope, just how many farads. The internal energy of a capacitor will be given as U, and often U sub C, just to be like the energy in a capacitor. We're going to have a few different things that can store energy throughout this semester, so I'll have different subscripts. If you drop the sub C, it's not necessarily wrong, but it's just good to keep track of when later on in the same problem, I'm going to introduce multiple things. We're going to eventually get to inductors, and I'll have problems with capacitors and inductors, and they're both storing energy. So it's good to keep track of which one's for which. But we can say the energy stored in a capacitor will be given as 1/2 CV squared. 1/2 the capacitance times the voltage squared. And yeah, this just stores energy. That's what it's good for. Now keep in mind, we said that the charge on a capacitor is CV. And if you use Q equals CV, you can plug that into U in 2 different ways to get 3 different U equations. One with C and V, one with Q and V, and one with Q and C. Because if you just have pen, sorry, there you go. If you have this equation and this equation, those two can be put together to create anything else. One is just, solve this for C, plug in. The other one, solve this for V, plug in. Make sense so far? Now, it's all well and good to say a capacitor can store energy, which it's good because it's needed. It's how a lot of a capacitor is needed for electric devices. But before I get further on what we can do with the capacitors, I need to kind of do an aside and just talk about something else for a split second and then put it all together. You see, we're going to be talking a lot about electronics, electrical devices. This is storing electric energy, what we can do with the electric energy. And so what I want to do for a tiny bit right now is talk about circuitry. You've heard the term circuits before. You're probably mildly familiar with what a circuit is. But a circuit is a collection of objects, usually containing a source of electrical energy, such as a battery, connected to elements that convert electrical energy to other forms. That's a stupid way to say a circuit is something that uses energy to do something. You put in energy, it does a thing. What it does depends what you made it to do. Circuits is just all of your electronic devices. And right now, I'm going to talk about just capacitors in circuits. And we're going to get to other various pieces as we go. Of note, I would normally refer to most circuits as the circuit diagram. The circuit diagram is just a way to show the path of a real circuit, and it's a shorthand just to draw what happens. But that being said, as I introduce circuit diagrams, you're going to need to start recognizing the symbols on a circuit diagram. That various pieces are going to use set symbols to always mean the same thing. So you can draw out what's going on and recognize it. In a circuit diagram, just wires are just lines. But the ones we're talking about now will be capacitors, which will look like parallel lines of same length. And you'll also sometimes see batteries. Batteries, which will be a DC power supply, and I will talk about that in a second, will be two lines, one bigger, one smaller. The bigger line always represents the positive terminal of a battery. The smaller line represents the negative terminal of a battery. Until I say otherwise, we are talking about DC, and I want to say the difference between AC and DC, not for a few chapters, but I'm talking about something that gives a constant supply of electrons, a constant potential difference, that the voltage or potential or electric potential difference is constant, it's not fluctuating, has a set value and goes. For that, you need a battery or any other DC supply. So just assume that for now. What that really means, we're going to get to a little later. Some other symbols you might need though in a circuit is that means a light bulb, and sometimes you see switches, where switches are just represented as a piece that can open and close. It's going to be a lot more things we need for a circuit diagram, but we're going to introduce the rest of them later on when we cover them in the physics sense. Basically, next chapter and the chapter after, and then the few after that. Okay, so now that we have that, let's talk about hooking up capacitors. Well, actually, no, I got a little bit more on that. So I had this picture earlier, right, which is a charging capacitor, just two plates hooked up to a battery. If I wanted to draw that in a circuit diagram, it would just be this: a power supply hooked up to a capacitor. That's it. Thing is, circuit diagrams we do in this class would normally be pretty simple. More complicated than that one. That's way too simple, but normally not be that bad. But in all reality, circuit diagrams can get pretty crazy. And what happens with them would depend on, I don't even know off the top of my head what that one does. Well, it's a low noise microphone preamplifier. That's what it does. But I wouldn't be able to quickly work out how it works. Oops, did not mean to do that. Okay, fun fact, my scroll wheel goes through these really fast. Okay. Now, the thing I also want to talk about before I really explain what capacitors are. Is that a question or? I think that's a no.
I think it's some feedback.
Okay. That works. The thing I want to really stress before I get into how to use these capacitors in a circuit is just ways to hook them up. And Capacitors or any other electrical element can be hooked up in one of two ways, what is called parallel and what is called series. You see, if you want to hook multiple capacitors together, you can go about it two different ways. And this, what you see right now, is what is called series. If you want to hook two capacitors up to a circuit in series, what it means is you go from your battery to one capacitor to the other capacitor back to the battery. Series just means they're in a line with each other. Now, because of, if you were to hook something up like this to the battery, each capacitor would get a potential difference over them because each capacitor would be hooked up to the battery and cause a movement of charge. And it's actually kind of interesting what would happen. The negative terminal, oops, I clicked on the wrong spot. The negative terminal of our battery would cause this negative Q. The positive terminal of the battery would cause this positive Q. But the location of this positive Q so close to another plate would cause this guy to pull all of his electrons towards it. And where it would pull the electrons from would be from this. And so when you hook them up in parallel, just by charging the outermost plate, by charging this plate and this plate, what you'll have is that the middle two plates will charge also due to basically Coulomb interaction. And if you hook capacitors up in series, you can have two charged bits. Now, of note, the potential difference of the battery will be split between both capacitors. That the potential difference on capacitor 1 plus the potential difference on capacitor 2 will equal the potential difference of the battery. They don't each get the amount of the battery, but it gets split evenly. However, let's say instead of this setup, you hook them up like so. If you hook your capacitors up like so, where you go from the battery to both capacitors, and from the other end of the battery to both capacitors, this is called parallel. In parallel, the potential difference of this power supply is going to go both places at once. It's going to go from here to this one, and from there to this one. And likewise with the negative. I'm talking about drawing more lines. What happens is that all the positives are connected together. And where with series, I have the negative of one battery hooked up to the positive of the other. Here I have the both positives hooked up together and both negatives hooked up together. Now, series has a lot of interesting effects. One of which is that both capacitors will get the same potential difference, the same voltage as the battery. That whatever electric potential difference the battery has will be applied to each capacitor. Okay. Nope, I didn't say that yet. Okay. So going further with this, let's stick to the parallel for now. We'll come back to series. If they both have the same potential, well, if both capacitors are the same, they'll be the same. But if they both have the same potential, and let's say capacitor 1 and capacitor 2 have the same different value for capacitance, that means they don't necessarily have the same charge. When you put two capacitors in parallel, they will each hold a different amount of charge, unless they happen to be the exact same capacitor. Like if it's a 10 farad capacitor and a 10 farad capacitor, then yes, they'll have the same charge. But if you put a 10 and a 15, they will have different charges. The total charge stored in a series of capacitors in parallel will just be the charge of each capacitor added up, because each one will get charged differently. Keep in mind they both will have the exact same voltage though, and their voltage will be the same as that of the battery. So now for each one we can say that the charge on it is CV. So Q1 C1, Q1 is C1 V1, but V1 is the same as V, and Q2 is C2 V2, but V2 is the same as V. What I'm going to do with this is I'm going to talk about the equivalent capacitor. That's, hey, we have two capacitors here. Could we do the same thing with one capacitor? And the answer is yes, as long as we have the exact right capacitor. If I wanted to replace this with one capacitor, I would need a capacitor that uses the same voltage V and can hold the total amount of charge, aka Q total. It would be with something where Q total is C equivalent times V. But since Q total is Q1 plus Q2, which is C1V plus C2V, that means Q total can be given as so. And matching these two equations, that means the equivalent capacitance is C1 plus C2. Anytime you have multiple capacitors in parallel, will have, each one will have the same voltage, their charges will be different, and they will be the same as one equivalent capacitor that has this total capacitance equal to the sum of each individual one. Okay? Let's go back to series. In series, what we said is that they have the potential is spread out between them. But if you look at this the battery brings some charge to Q plus, some charge to, sorry, let me get my pen again. The battery pulls some to this plate and some to this plate. But what happens is everything's going to balance. That this negative Q plate is going to pull to charge this guy, which is going to pull to charge that guy, which pulls to charge this one. And what happens is in series, due to the fact that if nothing else, there's a wire in the middle connecting the two capacitors. Ooh, that says conductors. That's a typo. Let me fix that real fast. Capacitors, because that's a big mistake. Well, they actually are conductors, but it still works. Because the capacitors hooked up to each other, they're each going to get the same charge. That whatever the charge is on one plate is the same as the charge, whatever the charge on one capacitor is the same as the charge on the other capacitor. Now, it's kind of weird to say this because you're probably like, well, doesn't, the total charge of capacitor should be zero because it's plus Q one plate, negative Q the other plate. I'm just viewing Q as the absolute value of either side, not the total charge, but just like this is the charge of the positive plate. Now, I already said they don't have the same potential, but the total potential they get will be the potential of the battery. So if I wanted to find an equivalent capacitor for this, well, I could say V1 is Q over C1, and V2 is Q over C2, but the voltage of the battery is Q over C equivalent. That means the voltage of the battery can be put like so. And with a bit of algebra, you can get this equation. Anytime you have multiple capacitors in series, 1 over the equivalent capacitance is 1 over each individual capacitor. The inverse of the equivalent capacitance is the sum of the inverses of the capacitors that make them up. In summary, in parallel, all the capacitors have the same voltage. In parallel, the total charge is equal to the sum of charges. And this equation is equivalent capacitance. In series, they all have the same charge. Their voltages add up to the voltage of the battery. And their equivalent capacitance can be found in that equation. Now, what we're going to do with this is we're going to do a lot of solving for equivalent capacitances. And maybe what's the charge on capacitors? What's the potential on capacitors? What's the total energy stored in a capacitor? To do this, you're going to need a lot of recognizing what's in parallel, what's in series. Once again, parallel, the capacitors are attached, both ends of the capacitors attached to the same point. In series, only one end of the capacitors are attached to each other, and the wire passes through them. So, I mean, there's only two of you, so I'm just going to do this out loud. Is this parallel or series? Either one of you. Or neither one of you.
Parallel?
Yep, that's parallel. It's parallel. My circle's in the wrong spot because we have, get my pen again, pen. because we have it going, the wire going to both ends, to both capacitors, and then coming back to both capacitors. They're hooked on either side to each other. And that's what you're basically going to have to solve things. So I'm going to jump into our first example problem. And this one is a little, I'm going to do basically for the rest of today. And I know I'm only halfway into the class, but I'm going to kind of spend this. I'm going to go through, I think, only 2 example problems that aren't necessarily hard, but just kind of annoying, to be honest. And these are similar to what I put on the exam, although I put closer to this one on the exam. And what I do is I have the setup. A 36-volt battery hooked up to 4 capacitors. A 4 microfarad, a 2 microfarad, a 24 microfarad, and an 8 microfarad. And I asked, what's the equivalent capacitance? And what's the charge and voltage on each capacitor? So if I ask something like this, your goal should be step by step to make your way to one equivalent capacitor. And once you have one equivalent capacitor, make your way back to find the charge and voltage on each. This is gonna be honest, a really annoying, time-consuming process. Sorry. But we can use this to figure out exactly what was happening with the capacitors. So I'm gonna walk through this one. I said this is a kind of simple one. So I want to work this out to one capacitor. And what I can see is this 4 microfarad is in parallel with this 2 microfarad, which is in parallel to this mess on the end. The 2 capacitors on the right are in series with each other. I can tell the 2 capacitors on the right in series together because they're just hooked up one after another. And so I can say, okay, what's the equivalent capacitance of those 2? The equivalent capacitance of those 2 will go as 1 over the equivalent capacitance is 1 over 24 plus 1 over 8. I could use a calculator, but I didn't bother. I said 1 over 8 is the same as 3 over 24. Just did some math. So 1 over 24 plus 3 over 24 is 4 over 24, which is the same as a 6th. And so that isn't the equivalent capacitance. Saying 1 over the equivalent capacitance is 1 over 6 microfarads. So therefore, the equivalent capacitance of those 2 is 6 microfarads. And I can say this circuit right here is the same as this circuit, because these 2 capacitors are the same as one that's 6. Now it seems kind of weird. Why would you put in a 24 microfarad capacitor and an 8 microfarad capacitor if you just needed a 6 microfarad capacitor? But that's the way it works. Sometimes there's reasons to do it. Are we good so far? What that did, oh, and because I'm doing this on PowerPoint, right, is I got rid of this picture to do this picture. When you're doing these out, keep each picture. What you're going to do is you're going to work your way through a series of pictures, then make your way back through them. You'll see what I mean in a second. But always make sure you nice and neat kind of have each picture going through. It'll make your life easier. So what I'm going to do is say, okay, now that I know that's a 6 microfarad capacitor, now I have 3 capacitors in parallel. Because that's all it is, just 3 capacitors right in parallel. Equivalent capacitance, add them up. And so I can say my equivalent capacitor here is just going to be 4 plus 2 plus 6, which is 12. And can say that this setup is the same as this, because it's just 3 in parallel. And so that would be my equivalent capacitance. Now, I asked for 2 things, that and the voltage and charge on each capacitor. Now that we have a simple circuit, that's always what you want to go to. You want to go to a simple circuit with 1 capacitor and a battery. Once you have a simple circuit with 1 capacitor and a battery, and if you have multiple batteries, this isn't really going to work. If you have multiple batteries, you're going to have to do something we're not going to cover until next chapter. But now that I have it down to 1 capacitor and 1 battery, I can say, okay, what's the voltage and charge on each one? And what I'll do is I'll start by saying, what's the voltage and charge on that one capacitor, this equivalent capacitor? Because if this was the case, if that's all we had, I could say, hey, look, one capacitor hooked up. Well, that capacitor must have 36 volts on it. Because that's all it is. But really, that isn't one capacitor. That capacitor was made up of 3 in parallel. And if that capacitor is made up of 3 in parallel, well, in parallel, all the capacitors have the same voltage. And all the capacitors have the same voltage in the battery. So really, that one is made up like this. Well, each of them have 36 volts on them because they're in parallel. Now, charge on each, that's just Q equals CV. So I could say, okay, the charge on the first one is 4 microfarads times 36. So there's the charge on the first one. Charge on the second one is 2 microfarads times 36. There's the charge on the second one. Charge on the third one is 6 microfarads times 36. But I'm going to stop there because we didn't have one capacitor at the end. If you go back to where we started, that was 2 capacitors in series, really, right? That 6 microfarad capacitor doesn't really exist. That's just the equivalence. So I want to say, you know what? I should split those back up. I should say that last capacitor really was a 24 microfarad and an 8 microfarad. But here's the thing. Back when I had them as one of them, just one, I said that if this equivalent had a charge of 0.216 millicoulombs. Now that I split them up, these are in series. All capacitors in series have the same charge, and their charge is the same, the equivalent. And so I can say if when they were one capacitor, if it had a charge of 0.216 millicoulombs, that means when it's split into 2, each one has a charge of 0.216 millicoulombs. And if I know the charge on each one, I can get the voltage because voltage is Q over C. So I can say for one of them, it's 0.216 over 24. I'm dropping some prefixes to get 9 volts. The other one is 0.216 over 8 microfarads to get 27 volts. Now note, these two, and I'm going to kind of add a line here because I think it's a little messy, just to separate them. These two should have this, the voltages should add up to be the equivalent voltage. But one's 9, one's 27, that's 36, so it adds up. Cool. There it is. And that is how you do these problems. If I ask you for the charge and voltage on a series of capacitors, make your way down to a single capacitor. Once you make your way down to a single capacitor, you can then make your way back. I am going to do another one today, and I have a summary slide in a second. But is there any questions before I jump to that? Okay. So here's my summary slide. In parallel, you add up the capacitance, you add up the charge, but the voltages are equal. In series, inverse add the capacitance for the equivalent. The voltages add up, but the charges are equal. Basically, the process is work a way to find C equivalent, and then you work your way back. If they're in parallel, you use voltage. If they're in series, you use charge. Okay, I got 15 minutes left, and I'm going to spend this 15 minutes basically doing one problem that I made a really ugly one. This is harder than I would give you on an exam. So let's look at it. there's my setup. So I have 7 capacitors hooked up like so, hooked up to a 48-volt battery. And I said, what's the equivalent capacitance? And what's the charge and voltage on each capacitor? So I'm going to start with the equivalent capacitance. And we'll look at it and go, okay, what can I easily add up? And I'll say, okay, there's a lot of things I could start with, but I decided to start with 5, 6, and 7. Capacitors 5, 6, and 7 are in parallel with each other. So I can say, I have an equivalent capacitance that I called C567. Well, C567 is just the sum of capacitor 5, capacitor 6, capacitor 7, because they're in parallel. And so I can say that those 3 capacitors, capacitors 5, 6, and 7, could be replaced with one 12 microfarad capacitor, like so. Now, what I then did is I said capacitor 4 and capacitor 567 are in series. And so I can add them in series and say 1 over C4567, because I'm just going to keep adding numbers like this, is 1 over 4 plus 1 over C567, which is 1 over 6 microfarads plus 1 over 12 microfarads. 1 over 6 is the same as 2 over 12, so 3 over 12. But 3 over 12 is a fourth. So C4567 is 4 microfarads. And I can say that that entire middle line would be the same if I had only one capacitor. One capacitor that's 4 microfarads. And there you go. That middle line was down to 1 now. I can then go and say, okay, up top, 1 and 2 are in parallel. So 1 and 2 is parallel, I can add them up. C12 is just 5 plus 4, which is 9. So I'll reduce them to 1 capacitor. That gives me C12 and C3 in series. Well, series, that's another inverse thing. So C123 is 1 over C12 plus 1 over C3. 1 over 9 plus 1 over 3. But 1 over 3 is the same as 3 over 9. So it's 4/9. But it's not. That's 1 over C, so I got to invert it. And it can say that C12 and C3 could be replaced by one capacitor with a value of 2.25 microfarads. And now I just have 2 capacitors left in parallel with each other. It's even in parallel to make it easy. The equivalent capacitance, that's just the sum of the 2. So I'll just add these 2 together and get 6.25. And so I can say this entire setup is the same as this. That if I just had one 6.25 microfarad capacitor, would do the same thing. Are we good for working down before I come back up? These are no vectors. Okay, so that is the capacitance of C equivalent. Now keep in mind C equivalent was made up by 2 parallel capacitors. This is why I meant keep all your work. I made it disappear because I only have so much space on the screen, but I'm going and just pulling back the figures. If you work down a page, then work back up, you can always look back at your photos. But C equivalent was made up by C123 and C4567. Each of those, they're in parallel with each other. Because they're in parallel with each other, they each have the same, they each had the same voltage. That the voltage on 123 equals the voltage on 4567, which was the voltage of the battery. I can get the charge of each one too. Q equals CV. So Q123, there you go. We can solve for it. Q 4, 5, 6, 7. There you go. We can solve for it. So let's put that information on my graph. Now I'm going exact opposite order I did before, so I'm going to do 1, 2, 3 next. What I said 5 minutes ago was that C123 was made up of 2 in series, C12 and C3. Because they're in series, they each have the same charge. That means C12 has 1.01.25 microcoulombs, and C3 has 1.01.25 microcoulombs. So I'm going to just drag those values over and say that's the charge for both of those. Using that, I can find the voltage on 1, 2 and the voltage on 3. The good news is we finished one capacitor. We got C3 worked out. We got one. But that's the voltage on those two. Let's look at C12. C12 originally was 2 capacitors, C1 and C2, that were in parallel to each other. But they're in parallel to each other. That means they each have the same voltage, the voltage of the equivalent capacitor. If C12 has 11.25 volts, that means C1 has 11.25 volts, and C2 has 11.25 volts. Side note, these slides sucked to make in PowerPoint. And I know the voltage on both. If I know the voltage on both, I can pretty easily get the charge on both because Q equals CV. And there you go. I now know the charge and voltage on 1, 2, and 3. Meanwhile, I told you, this one's a long one. I can go back to 4, 5, 6, 7. 4, 5, 6, 7, I doubt you remember because it seems like ages ago. 4, 5, 6, 7 was made up by some parts in series that looked like this. It was C4 and C5, 6, 7. So what I can do is say, okay, these were in, what am I doing it there? Oh, I see. These were in series. That means they each have the same charge. But the charge on the charge on 4, 5, 6, 7 is 180 microcoulombs. That means the charge on capacitor 4 is 180 microcoulombs. That means the charge on C567 is 180 microcoulombs. I was running out of space, so I moved some stuff up top. Literally, it's because I was continuing to put them all on the thing everywhere like I have here, but it started getting so messy that I'm like, screw it, let's just put everything on top. But there we go. That's the charge on both of them. If I know the charge on both of them, I can find the potential on both of them because V is Q over C. So the potential on 4 is just Q4 over C4. The potential on 5, 6, 7 is Q 5, 6, 7 over C 5, 6, 7. So I'm going to once again move Q4 and V4 to the top because space. Oops. And say, okay, we got this 5, 6, 7. And the 5, 6, 7 had a 15-volt potential. But 5, 6, 7 wasn't just one capacitor, it was 3 capacitors, capacitor 5, 6, and 7, that were hooked up in parallel. That means that they're hooked up in parallel, we know the voltage on each one. That the voltage on 5 equals the voltage on 6 equals the voltage on 7 equals the voltage of 5, 6, 7. And I can say that each one of those has a 15-volt potential. And if I know the potential in each one, Q equals CV. There's the charge on 5. the charge on 6, the charge on 7. And that was all the way down. That can tell me, hey, here's what the values were. And this is the main reason you would sometimes deal with this parallel and series stuff. You might want certain charges and certain voltages in set places. And you can do that by putting together something like this. It's not necessarily difficult, but it's annoying. And it's really easy to make a mistake. Because if you make a math mistake anywhere through all of the thing I just did, it's going to keep paralleling through all the way through. And they're kind of time consuming too, to be honest. I mean, I just spent 10 minutes on that problem. But that is the process. You break it down to one capacitor, and then you slowly split it back up into equivalent capacitors. Any questions? Okay. I'm going to stop there because I feel like if I try, never mind that I'm done, but I feel like if I make any more math happen after doing that shit, it'll probably make a brain explode. Practice problems are being uploaded in 4 minutes at 3:50. We'll cover examples problems on Friday where I would do some things with potential, and I have at least one of these in there, so that's fun. Get to see me do it live and confuse myself. But yeah, that'll be that. Don't forget homework due tonight and lab due tomorrow, assuming you're watching this on the 9th. Have a good day.